Welcome to Ask and Learn.
So for this roller coaster problem, we can draw a force diagram at the bottom of the loop. So at the bottom of the loop, the force diagram, the two forces acting, here we have the normal force and we have mg vector. At the bottom of the loop here, I'll draw it slightly bigger. So the net force at the bottom is Fn bottom minus mg, which is equals to the centripetal force, which is mv bottom squared over r. So that implies that Fn bottom, which is the normal force at the bottom, is given by mg plus mv bottom squared by r. So that is the equation at the bottom of the loop. Now at the top of the loop here, at the top of the loop, so we have the roller coaster in this condition here. The forces are normal force at the top, and we have the gravity vector, force of gravity vector, which is Fg, which is equals to mg. So net force on the top is equals to the normal forces on the top plus mg, because they are in the same direction, and that should be equals to the centripetal force, which is mv top squared by r, which implies that the normal forces on the top is equals to mv top squared over r minus mg. So we got the two equations for the normal forces on the bottom and on the top. Now we assume that the roller coaster, when it goes on the top, it doesn't fall down, which means that the normal forces on the top are greater than 0. So we can also say that v top is greater than rg, basically. So now we'll apply the law of conservation of energy. The level 1 represents the coaster at the bottom of the loop. So this is the level 1, and this is level 2 at the top of the loop. And the level of the bottom of the loop is 0 location. So the roller coaster, is going from the bottom to the top here, and the level of the bottom is 0 at 0 location. So y is equals to 0. And at this location, the y, which is the height gained, is equals to 2r. So the total energy is conserved at these two locations. So we write down E1 is equals to E2, which implies that at these two locations, half mv1 squared plus mgy1 should be equals to half mv2 squared plus mgy2. So if you plug in the values in this equation, which implies that you will get v bottom squared is equals to v top squared plus 4gr. So you can just plug in the value. Just plug y1 is equals to 0. Okay, y2 here at this location here is 2r, and we can actually calculate the v1 and v2 at two locations, and the relationship will be this: vb squared is equal to vt squared plus 4gr. And what they're asking here is the difference in the apparent weights. So the difference in apparent weights, is actually the difference in the normal forces, because apparent weight is what you feel, and you feel the normal force. So it is the Fnb minus Fn top. So what's the difference in these two? So if you look at these two equations, so you will get mg plus mv bottom squared by r and subtracting it to mv top squared by r minus mg. So I just go on to the next page for this. So if you rearrange this equation and solve that, so you'll be getting 2mg plus m v bottom squared minus v top squared over r. So that should give you 2mg plus m, and we know that the difference in v bottom and v top was already equals to 4gr divided by r. So that should give you 6mg. Now as you can see that this result what you have got does not contain r, there is no r here and there is no v here. So therefore this answer does not depend on the size of the loop and also on how fast you go on the loop.